finally, Lami's theorem brings together the triangulation of forces and that sine rule process that we've been doing. And instead of creating the triangle of forces, what we're saying is that P over theta, sine of theta, is equal angle Q. I'll call it theta 2, which is angle force R over theta 3. So in actual fact, it's just the force over its corresponding angle, sine of its corresponding angle, they all balance out. Okay, so once you get your triangle of forces, well, not even a triangle of forces, you draw your diagram to get your forces up, you can just apply a sine rule to it. Okay, so if we just have a look in here, the angles between three forces respectively. So if I draw a 10 Newton force, hang on, let's just pause that. Now that we've got that a little bit tidier, there's my forces. So we've got the angles acting between 100 degrees, 120 degrees, so that's 220, so that must be 140 degrees, yeah? So what my Lami's theorem tells me is that P over sine of 140 is equal to Q over sine of 100, which is equal to 10 over sine of 120. So it's just the force and the angle opposite the force. And so from there, it's just rearranging. P is equal to 10 times sine 140 over sine 120, and Q equals 10 times sine 100 over sine 120, which equals, we get 7.42 kilogram weight of force and 11.37 kilogram weight of force. Yeah, so it really is just, once you've got that set of forces the diagram of forces set up, the three forces, we can use them. So if we have a look at a couple of familiar scenarios here and solve them using Lami's theorem. So here's our string again. It's been fixed. It's a 10-meter string. Two strings of length 10 meters are attached to 2 points, 12 meters apart. So there's my sort of 12, 10, 10. So halfway is 6. So it's a 6, 10 from Pythagoras' theorem, that makes that 8. So we happen to get a nice right angle triangle. If we didn't get a right angle triangle, you might need to use a cosine rule, which I doubt if we'd have that this year to determine the other angles. But since it's a right angle triangle, I know that cos of theta is 3/5, so the angle we're interested in is 53.13 degrees. And then I've just got my diagram set up in the same way. And so I've got that green theta here. We know that that's 53.18 degrees. So plus 90 makes it 143.13. So the two big angles, 143.13 degrees. And as it turns out, we know that our angle in between will be 73.74, that looks like. Okay, so now we've got our three angles, so 20 over sine 73.74 equals T2 over sine 143.13, which equals T1 over sine of 143.13. As we'd expect, since these strings are the same length, the tensions in the strings are going to be the same. So T1 is the same as T2. And we just use one of those, rearrange that, 20 times sine 143.13 over sine of 73.74 will give me a tension of 6.25. I've got newtons there, it probably should be kilogram weight. So let's fix that up, kilogram weight, okay. Final one. Again, familiar scenario. We happen to have one line of a string is being attached to a point A on a vertical wall. A on a vertical wall. Mass of 5 kilograms hanging vertically. The force acting horizontally so that the string makes an angle of 30 degrees. So if we just work with that, obviously the angle in here is going to be 60, the alternate angle is 30. And so we can work out the size of the angles in between, isn't it? So there's my P force. The angle opposite the P force is 90 plus 60. My 5 Newton force, the angle opposite that is 30 plus 90. And my tension in my string, well, they're acting at a right angle. All right, so then once again, we can just pair up our key values and work out that our P force is 5 root 3 on 3 kilogram weight, and the tension force 10 root 3 on 3. If we change the scenario slightly, again, there's my point A. Again, the angle we create is still 30 degrees, which means the angle down here is 60 degrees. So if we work out some big angles here, obviously we've got 90 because we were told. We're going to have, what's that, 120, 150. And then same sort of thing. So P over sine 150 is equal to 5 over sine 90, which is T over sine 120. And again, rearrange to get our final tension and the force required to hold the string at that angle. So again, once we've got our scenario there with our strings and with the string systems and our particles in equilibrium, we can often use Lami's theorems to solve for that. Okay.